Hi, I'm Nishi Ahuja, and I'm Senior Principal Engineer with Intel, and I'm going to be presenting Advanced Liquid Cooling Rack Design for JD.com Data Center. This presentation is being presented on behalf of JD.com. What we are going to cover is we have been working with JD.com for an entire year, and we have accumulated a lot of experiences. So this presentation will cover some of the experiences, the best known methods, and the rack level design and architecture. In this, I will be covering liquid cooling system architecture. The architecture starts with the cooling tower, which is at the top of the slide that you see, which is exchanging heat between the facility and outside air. And then you have the cooling distribution unit, which is exchanging heat from the racks to the facility through the manifolds. So the rack has manifolds, which is an intake manifold, as well as the return manifold. So return manifold will take the hot liquid out to the facility. So the facility water gets heated and it goes to the cooling tower. Cooling tower will in return send liquid, cold liquid back to the racks. So then what is happening is that the liquid around the hot components are capturing the heat and then returning that through the return manifold and that to the facility and cooling tower. So now let's start looking at some of the best practices that were deployed to select the best cold plate. They looked at several cases, and they formulated a equation that they used to find out the optimal design. And this equation has a flow rate, it has the pressure drop across the cold plate, and the thermal resistance. So these are the three parameters that they took into account to determine the optimal design. So let's say if the thermal resistance was low, then the design is optimal. If the flow rate was low, then the design is optimal. Or if the pressure drop across the cold plate was small, then it's an optimal design. So based on this equation, JD.com looked at those 6 cases and determined which were the best optimal designs. So if you look at the case 6, is an optimal design if your flow rate was between 0.5 to 1 liters per minute, and your case 5 was optimal if your flow rate was 1.2 liters per minute, and your case 1 was optimal if your flow rate is 1.5 liters per minute. So basically this was the equation that they defined to come up with an optimal design. Now in order to come up with the memory cold plate, what did they look at? So they looked at the dim pitch. So let's say if the dim pitch was greater than 0.35 inches, then they used a flattened liquid channel loop for the design. And then if the dim pitch was between 0.3 to 0.35 inches, then they used heat pipes connected to the manifold. And then for the dim pitch, which was between 0.2 to 0.3 inches, they used heat sinks, which was cooled on the side by the liquid. So now let's look at how they came up with the pipe selection or the tube selection. They looked at 2 criteria. One was looking at the performance, another was looking at the reliability. In terms of reliability, they are looking at if the pipe gets damaged, and then for the reliability, for the performance, they were looking more at the evaporation rate. So based on that, they tested 5 pipes based on those 2 criteria, and more details are in the white paper. Now another best practice that they looked at, so if they have to carry flow parallel to multiple components, then they came up with the best practice that they need to have a manifold which is internal to the server. And in this design, you will see one of the fans is removed from the server to include that internal manifold. So this design is very good for hybrid cooling, where you can have liquid for the CPUs and air for the memory. So basically, to get flow to multiple components and parallel path, you will have to have a manifold which is inside the server, and one of the fans is removed in that case. Now, another thing which is very important in liquid cooling is leak detection. So in order to detect the leak, they deployed a wired sensor. And this wired sensor was basically looping across the tube as well as through the cold plates. And then when there is a change in resistance, that means there is humidity detected. So that means this sensor helped them to identify the humidity, which identified any leakage in the pipes or in that server. So in detail, the white paper will cover a lot more details about this cold plate technologies that we have deployed, as well as the best practices, as well as some of the quick connect technology, as well as the proof of concept at JD.com. Mm-hmm. So I would like to end my session with the call of action. I would like you to come together to the working group and work on this technology together and standardize this. We would also like to post this white paper on the wiki that is mentioned here. And also, if there are any additional questions, you are open to contacting me or the other author, which is JD.com, for any additional questions.